हेलो। नहीं नहीं, वो अभी तक गया नहीं है।
আচ্ছা, আমি আসছি, একটু এখানে সেটআপ, হ্যাঁ একটু সেটআপ করে, হ্যাঁ আসছি আসছি।
Hi, Sangheeta.
Hello. 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 Check. Check. Hello. 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 Check.
Yeah.
Hello.
Welcome to the post-lunch session. Now we have a tutorial entitled Unveiling the Code of Neuronal Activation Patterns by Dr. Sangheeta Roy of TCS Research Lab, Kolkata. And I would like to request Professor Raghunath Chatterjee of Indian Statistical Institute to please come on stage and chair the session for us.
Good afternoon. So it is a great pleasure to have Dr. Sangheeta Roy from TCS Research Lab with us today. So just to give you a very brief introduction about the research work that Dr. Roy is doing. So Dr. Roy is currently the researcher in TCS Research Labs. He's working there from since 2012. And Dr. Roy is one of the expert in the field of machine learning, signal processing, and computational neuroscience. And she is currently working in a very interesting area. So there are certain neurological disease conditions where actually the regular medications as well as the different kind of regular therapies they cannot work. So there, the only alternative is essentially use of the brain stimulation therapy, and that is a non-invasive process. But one of the very important aspect is like if we can develop something which can be simulated so that the clinicians will be greatly benefited. And she is currently working in that area, and she is developing a simulation platform where such system can be simulated using brain computation modeling. So Dr. Roy did her PhD in 2018, and she did her MS and BTech in computer science, and she has been working in TCS Research Lab since 2012. So Dr. Roy, the podium is yours. And probably Dr. Chakraborty and Arvind Kumar is going to ask, right? Okay. Okay.
Can you hear that?
Yes, I can hear you.
Arjun?
Uh,
Yeah. Yeah. Thank you, sir, for introducing us. So today we will be discussing and the unveiling the code of the neural activation pattern, and we discuss about some basic kinds of things, how we develop from neuron synapse and how we convert it into the computational model, and how we can use those things to discover some underlying mechanism of some kinds of neurodegenerative disease, and how you can correlate some brain signal with those computational models. So we'll try to cover this thing, and we'll try to show some hands-on. So Kingshu will start first. So, yeah.
Good afternoon, everybody. Today, we will cover these topics during our presentation. And first of all, thanks to the organizer who gave us this opportunity to present our stuff today. We will gradually cover these topics for the next 2 hours. It might get longer by 10 or 20 minutes. We will like to take the questions at the end of the session. Let's start this talk. Today we will start with our very familiar and fascinating world of neuronal networks. In this room, everybody, I guess everybody is familiar with the word artificial neural network or the deep neural network. They are basically our brain-inspired models. Now, in simple terms, ANN or artificial neural network are composed of connected nodes. We call them neurons, which are again organized neatly in layers, sometimes in hidden layers. And the learning in the network happens through adjusting the connection weights or parameters and implying a few functions that can spot pattern in the incoming data or input data. But they are brain inspired. Now the big question lies, are they truly like brain? Brain is basically a very complex network. It is indeed a marvelous structure with billions of connected neurons. But these neurons chat with each other using electrical and chemical signals. Brain networks are yet complex but dynamic in nature. It can handle enormous number of functions in every situation seamlessly. So here's the coolest part. We can imagine the modern day so-called advanced machine learning neural networks are doing are far away from the actual brain networks. But in today's world, spiking neural network, or in brief SNN, are the closest in mimicking how brain works. They use the time-based calculation instead of the continuous variable and spike train kind of mechanism. Now this spike train I will cover later in this section, in this tutorial, is basically how brain sends or manages information. Now, unfortunately, this SNN also today mainly rely on the basic structure of artificial neural network rather than preferably copying the brain's complex and dynamic networks. But the hope is SNN is the first stepping stone towards making something that acts just like brain. Now, what is brain? Let's speak into the brain's world. In adults, generally the area of brain falls between 1200 to 1300 or 1400 cubic cc and weighs around 1.5 kg. This is the statistical parameters, right? But it also varies based on gender, age, and uniqueness of person's brain. And get this brain is complex and it is packed with 86 billions of neurons. And this makes brain the superpower, right? And here is where it gets even more fascinating. Brain is not at all a one size fits for all model. It is very much complex but personalized. It varies from person to person. In fact, for a same person with ages, different parts of the brain acts differently. Not only that, another term usually coined with brain, that is called mind. Now, brain and mind are two connected bodies. They act differently. We can think brain is basically like a supercomputer and is a physical stuff, and mind is its abstract way of implementation. Mind is all about thinking and being aware of. Or you can imagine the other way that mind is a particular way of brains showing off all of its clever stuff. But both are related. Once we study brain, then in future we may need to study or we should study the mind. Now, how brain works? We are talking about the brain. Now, how brain works? Before going into deep, we will start with how brain is made of. You know, brain has a very tiny messenger particle. We call it neuron. And through neuron, brain communicates with the other parts of the body. It's basically a cell. Now, briefly, neuron has three structures, three parts. Main one is the cell body. It's like headquarters. It summits all the incoming information and sometimes take also the decisions. These are the branches. You can see these branches we call dendrites, which collect or listen information from other neighboring neurons. And these longer tail axons mainly passes information or messages to the other neuron. Now, once we are talking about this message passing, but neurons don't touch each other to pass that information. Basically, we use messenger-like molecules, which we call neurotransmitter, which traverses along these synaptic tiny gaps called synapse to pass the information to the neighboring neuron. It's like passing notes inside a class, right? Now, how this neuron actually works. So, in order to explain this, we can take an analogy from our real life world. For example, we can think neuron as a bustling office, and sodium and potassium ions shown in this picture are the busy workers that works inside and outside the neuron. Inside of the neuron, it's filled with cytoplasm, and outside is basically the extracellular space. Now, since it is like busy workers, we need to have a supervisor, right? And this pump acts like a supervisor, which makes everything right or everything balanced inside and outside the cell or the neuron. Now, how pump does that? Pump uses energy, which is called ATP or ADP, to make everything right. Because these sodium and potassium ions are not very good. Sodium ion just wants to come in, but pump says, no, you can come out, or you can go out. And the potassium ion wants to come in, wants to go out, because they are very extrovert, and this pump says, no, you can come on in. So pump acts like a supervisor. or acts like a traffic controller, which ensures right amount of potassium and sodium ion present inside or outside of the neuron. So it keeps everything right so that the neuron can send message or receive message from other neurons. Now, when neurons in a very calm or chilling state, or it is not sending any message to the others, we call neuron is in a resting state, or neuron is resting. In this time, the sodium ion is more outside and potassium ion is more inside. This creates a change in the membrane potential or charge difference across this membrane. And it makes inside of the neuron more negative with respect to the outside one. Okay, which one? Yeah. Now, when neuron receives a message from a neighboring neuron, then it opens its gate so that sodium ions can rush in. We call this phenomena as depolarization. It means it increases the membrane potential, increases the positive, it decreases the negative charge of the inside of the neuron, and it makes it bit positive. Now, if this depolarization goes far enough, then neuron reaches a particular level where it can say something or it can fire. Now it fires the action potential. This time, the gate is so open that a large amount of sodium ion goes inside and makes inside of the neuron positive for a short while. Now, after this excitement, neuron again goes back from positive charge to the negative state, negative resting state. We call this phenomena as repolarization. Now, sometimes neuron goes far below the resting state. And during this hyperpolarization phase or this hyperpolarization makes inside of the neuron so negative that it will take much more time to respond to other jolts or other incoming messages. So we can think this phenomena using by graphing the membrane potential itself. For example, if we think neuron is a quieter room like this one, and jolts or in the form of any signal or spikes, specifically spikes comes in, then neuron awakes from the resting state or the calm state. And these jolts will make neuron makes the neuron more active, and it goes to a particular level. When this phase is called depolarization. When it hits that level, it fires the message or it says something, and after this excitement, neuron again repolarizes to resting state. Sometimes it goes below its quieter state or it becomes more quieter than before. We call this as a hyperpolarization. But now you know all of this phase occurs because of these chemicals moving around. Now this is the gross or approximate dynamics that happens inside the neuron. We can model this using a level of complex electrical or electrochemical circuits. So now these electrical or electrochemical circuits are mainly governed by n-dimensional differential equations. So we can use this equation or circuits to model or computationally model the brain complex networks. Now you know brain is packed with 86 billions of neurons, and these neurons exhibit a good amount of heterogeneity in terms of function, structures, or properties. in fact in uniqueness also. This creates or this makes the brain network a bit complex, right? Some neurons can generate the firing pattern, generate spikes of fires at regular interval with constant rate. That means the time duration between two spikes or two signals or two firing are constant. Some fires at irregularly, some fires in burst. So these variety, not only that, the structure also, you can see the structure also varies, or the properties also varies for the neural models. This variety ensures how information is transmitted or encoded in the brain. Now you have already heard some term like ReLU or tan hyperbolic or sigmoidal as an activation function of artificial neural network. They are very simple and contrast starkly against the diverse and complex firing pattern of these neurons commonly seen in the brain. Now, capturing these dynamics and adaptability of these neurons are not very easy. So, computational neuroscientists often model neurons based on the functional behavior or the behavior of the brain, or the brain dynamic needs to be simulated based on their requirement, based on that requirement. If you need something for simpler task, or the higher level abstraction suffices for your application, then you can go for the much simpler model like McCulloch-Pitts. But they are very computationally less. They are not computationally expensive, this kind of model. But if you need a precise simulation of the behavior, or if you need to synthesize something that is very complex, then you need to use a more complex model, and you need to incorporate the precise details of the neuronal behavior, synaptic properties, or the connection properties, and the neural dynamics also. So for example, if you want a very precise simulation, you can use models like Hodgkin-Huxley, Morris-Laker, Wilson, Ichkevich, etc. And these neural models, once you have them, this is computationally expensive. You need to have some computational power to execute such model or generate something using this model. Now, until this, we have discussed about the mathematical modeling of the neuron. Now, are these realization of neuron using electrical circuits? But are these very straightforward? In one word, answer is no. One can define a neuron using a set of dynamical equation or using a single circuit or using a single network. This is called point neuron based approach. But neuron has a larger size. So you can divide the neuron into smaller parts, and we call it as compartment, and study how these compartments work together to realize a function as a single neuron. This is multi-compartmental approach. Since it has multi-compartments, so number of parameters will be higher. Now you know in brain there is a term called nuclei, and each nuclei is basically a population of neurons. Now, implementing a nuclei using this multi-compartmental based approach is not very easy. It requires a lot of parameter tuning. So the task is more challenging using the multi-compartmental approach. So that we can see in brief or in very, sorry. Then you can see in this model that this is point neuron based one, and the left one is the two compartment based model, this one. So you can see a starting difference between the complexity levels, right? It needs lots of parameter tuning compared to this one. So based on your need, you need to choose a model. Now, fortunately, a few neuronal simulator available in the market like NEST, Brian, Neuron. You can use this neuronal simulator to build your own neural network. So you can use this the higher level APIs, or you have the freedom to use the higher level APIs to build your single compartment or multi compartment based model or neural network instead of writing everything from the ground up. Now, how the information is transmitted inside a neural network, that is in the brain. We already talked about something or like spike. Now, transmission of information in the neuronal network or brain network happens through spike. This spike is nothing but a Dirac delta function. That means at t equals to 0, it has a value, otherwise it don't have any value. So a neuron mainly sends a spike along the axon, and this spike travels across a tiny gap or across the synapse to the neighboring neuron. The source neuron which sends the spike, we call them presynaptic neuron. Now, when another neuron, like this one, get the spikes from the presynaptic neuron, its membrane potential increases a bit, but temporarily. This increase we call postsynaptic potential. But if it is not getting any further spikes from the presynaptic terminal or other neurons, then its membrane potential again goes back to the resting state. That means we call it is as a failed initiation. But if the spikes from the presynaptic terminal keeps coming in, then it adds up inside the secondary or receiving neuron. It adds up more, neuron gets more charge, and it goes towards a particular level, that is threshold. Now, if the charging is enough, then it can also emit spike to the other neuron. Here you can see that since the spike is coming at the regular interval, it adds up and it goes to a particular level, that is threshold. When once it crosses the threshold, it creates a spike. So you can see in some cases, if the spikes or the incoming signals are not good enough, it can stay below the threshold. And this we call as a sub-threshold regime, where the membrane potential will fluctuate, but neuron cannot fire the spike. But if it crosses the threshold, then it can emit the spike. If we call it as a suprathreshold regime. Now, brain has several stimuli which can generate this kind of behavior. Like one of them is hyperpolarizing stimuli, which is like it calls the neuron come down, it makes the inside of the neuron very negative, and neuron takes more time to respond to other messages. Now, another stimuli is the subthreshold or depolarizing stimuli, where the stimuli activates the neuron. Neuron arises from its calm or resting state and goes towards the threshold. That means there is a chance that neuron can fire the spikes or generates the action potential. And suprathreshold stimuli basically is the one which is strong enough that pushes the neuron to fire. That means using suprathreshold stimuli, we can expect to see a dynamics in the subthreshold regime. Now there is two regimes you can see. One is subthreshold and another is the suprathreshold. That means below threshold and above the threshold. Once the neuron, given the stimuli or given the input current, once the neuron is a subthreshold regime, then with the increase in the input or input current, we can expect there is a change in the steady state membrane potential voltage. So we mainly study this IV curve, where I is the mainly the incoming current and V is the steady state voltage. Then the neuron is in, we can say, in the subthreshold regime. But if it crosses, if the incoming current is so strong enough that it can generate the spikes, and we can start it from there and increase the strength further and further, more and more, then the number of spikes will increase. And sometimes it get always be saturated. So then we can study in the superficial regime, we can study the IF curve, where I is basically the x-axis is basically the input current, and y-axis number of spikes per second in a till this point we already talked about the stimuli part. We talked about the synapse, how information is passing through the network. Now we will give an overview how neural modeling can be developed. So here we will start with a very simpler one, which is called leaky integrate and fire neurons. But this neural model we can use to generate lots of dynamical neuronal dynamics. So now the question is how this leak or leaky integrate and fire neural model works. So to describe this, we can take an analogy from like we can think neuron as a bucket of water with a tiny hole at the bottom. Now, this neuron bucket starts with some water inside. It means it has some resting potential. When signal or water comes in, it ends up inside the water. Slowly, the bucket slowly filling up. Now, here is a cat. It has a tiny hole at the bottom, right? So, in the absence of any further incoming spikes or the water, it leaks out. But if the water comes in a regular interval or continuously, then it builds up inside the bucket, and neuron membrane potential increases and going to a particular level. When it hits that level, then the bucket cannot hold it back, it spills out. Meaning the neuron fires the action potential and it is again reset back to zero or resting state. We can model this behavior using a simple electrical circuit, where you can see this is the RC circuit that we have already studied in our graduate school. This R is basically the resistance and C is the capacitance. R slows down the electricity in that circuit, where capacitor stores the charge. Now this is basically a battery connected to the circuit. Now when the lever is not attached, then this circuit maintains the resting potential. Now when the lever is in closed state, I flows in and capacitor starts to charge. That means we can, just like membrane potential of the neurons increased when it is getting stimulated or when it is getting signal from the neighboring neuron. Now, if this neuron circuit keeps getting the signal, then the capacitor charges are more and more, and it is going towards a level where it can say something. Now, when it's hit that, just like the membrane potential increases towards the threshold, because the signal comes in at a regular interval. Now, when it hits that level, that means that threshold, the capacitor starts discharging or releasing its entire charge. Then we can say neuron fires and it is again reset back to its resting potential. But it is always not that case. If the signal is not strong enough, then it can initially temporarily rise, again then it can go back to the resting state. This is basically leaf, how leaf works. And we can model this thing using this simple dynamical equations or differential equations. Here also you can see there are two parts. One is the substitutional changes, where you can get the changes in the steady state or the voltage. When it crosses the threshold, we can get the firing patterns. That means we can get the number of spikes the neuron emits. But unfortunately, this leaf is so simple, it can only generate the regular firing pattern. Now question is, what is regular firing pattern? Regular firing pattern is nothing but a clock ticking every seconds without any surprise. Or you can think the train comes at the platform after every 30 seconds. This is very much predictable. But the adaptive firing pattern is something unpredictable. It's like changing rhythm in the traffic. Or instead of the train coming at the platform after every 20 or 50 seconds, it comes initially after 5 seconds, then 10 seconds, then 15 seconds, and then more. That means this firing or this spike interval are very dynamic, yet it is complex. But we cannot explain this dynamics or it cannot generate this spiking pattern. So here we need more complex tool like adaptive exponential kind of neural model. We call it ADX. It can generate this kind of irregular firing pattern where interspike interval can vary with time, or it can generate a burst where you can see for a very short while neuron generates a lot of spikes. So ADX can generate that kind of thing. Now, how ADX works? ADX is basically this kind of model. It borrows the same membrane potential dynamics from the leaf, but it adds a bit more. This FV, you can see, this is basically the leaf equation. This is the leaf equation, right? Now, if you can see ADX, this FV governs this. Now it adds another term, this one. This is basically the delta T. This delta T basically governs the steepness of the membrane potential increase or the speed of the roller coaster ride. Now, this delta T is basically to controls the slope of the increase mainly. Now, it also has a recovery variable. This is the adaptation. And this W controls the adaptation. Here comes the adaptive part. You can see this adaptive exponential recovery of that neuron is the way the neuron says, I will bounce back or recharge after the fire. But this recharge or this bouncing back is not same always. It varies with time. It's like, and it depends upon what's going inside the neuron, because you can see this recovery is also a function of this membrane potential difference. That means it depends upon what's going inside at that point of time in the neuron. These two equations then governs the adaptive part of the leaf. Sorry. And so it's like battery charging very fast initially, then it's charging slowly. So recovery also varies with time. So this is about the addicts. Now, once we have the addicts, so how we can code them? So initially we need to define the how neuron properties like what could be threshold, what could be a resting potential, right? This parameter you need to first define. Then you need to define the membrane potential dynamics. Once you once you have done that, then you need to think when the neuron reaches the threshold or enters into the subthreshold regime, then how it can behave. So here it generates the spikes. So we add the spike count, and then again neuron is reset to its resting potential. But this is adaptive, right? So this time this resting potential or the where the neuron is resetted will change the adaptation current, and this adaptation current is driven by these dynamics. And you can see this adaptation current dynamics also depend upon the membrane potential dynamics. So these two dynamics govern the ADX. So in this way, we code the ADX model. Now we will see some of the firing pattern that can be generated using the ADX. Yeah, I'm sure. Yeah, because she will share. Yeah, no, she will share something. Yeah. Please share. Thank you. Yeah, it's not visible over here. Yeah, we can visit it. It's not coming out. Yeah, yeah, no, it's done. Yeah, so first we will see when a pulse input is given, how ADX can generate the spike pattern. So you can see uh, if the pulse is given and pulse duration is very short, it's around 10 or 15 milliseconds, then you can see there is a spike generated by the ADX. And in the ADX dynamics, there are only extra two terms, that is called delta T, that means it's control the slope, and the recovery part, that is W. If delta T tends to 0 or W is not there, then ADX will become the leaf. But here, so then there should not be any adaptation or slope. But here, since it's a pulse, so we can't expect to have a much difference in the firing output. So leaf and ADX almost behaves like a same thing. Now, if we give another DC pulse, sorry, DC signal, DC means from 0, the current input is increased to 600 picoampere. And you can see there is a change in the firing pattern, where the ADX neuron fires in burst. For every burst, there are only 3 spikes mainly, but in leaf, we are not getting any adaptation. So there is almost a regular firing pattern. Go to DC2. It is another set of firing where you can see there is an initial adaptation happening, that means initial ISI or the interspike interval in the ADX is very less and it gradually increasing, but in leaf there is always a regularity. That means there is no adaptation. This is interesting. First, we give some hyperpolarizing stimuli. That means we intentionally push the neuron below the threshold, below the resting potential. Now we release that stimuli. So in ADX, you can see some spikes. We call it as a rebound spikes, hyperpolarization induced rebound spikes. But in leaf, it cannot generate that stuff. Reset it, first reset it. This is IF curve. So here what we did, we basically giving a lot of DC currents ranging from 500 to 700 picoampere, and for every current we are just counting the number of spikes emitted by that particular ADX model. Now, in the membrane potential, you can see there is a superimposition of the spikes for different inputs. But in the IF curve, you can see how the firing pattern increasing with this input currents. Yeah. This is basically a demonstration of how we capture the subthreshold dynamics, where we increase the input currents, and we are very sure that neuron will not emit any spikes. So we can then we record the steady state voltage or steady state membrane potential in millivolts and plotted it. You can see with the increase, the neuron steady state membrane potential is also increasing almost in a linear fashion. And sometimes it will cross the threshold and it will emit the spike. And for this current, where it crosses that threshold and start emitting the spike, called it as a Leo wave. Next to you. We have already seen this. Here you can see the adaptation, bursting, but in leaf we cannot expect that. Now ADX has a numerous parameter, so we can change those parameters to simulate our desired dynamics or simulate the behavior we want for the particular neuron. I am giving you an example. If B is changed, that means B governs the adaptation part. If B increases, the number of spike will decrease because after every spikes, B is reset back to W minus B. So increase the B a bit or more. Yeah, similar. You can see there is a decrease in the spikes. Similarly, if A is increased, A is the recovery current. So if I increase the A, that means recovery will be higher. So we can't expect to have more spikes. So just increase the no spikes. So in this way, we can tweak each of the parameters and try to simulate the behavior we want. And in fact, we can automate it using some optimization algorithm to match the morphological features of the output as with respect to the ground truth. This is all about the ADX. I will now we have talked about how neuron model is developed, or we can develop the neuron model. What are the complexities we have? Now, once we have the neuron, then we need to connect two neurons through synapses. And once two neurons are connected, we can connect n number of neurons to build a nuclei or a neuronal network. So my colleague will, Sangheeta will cover these two stuff, synapse and neural network behavior.
So Kinshuk has discussed about the basic element of the network, neural network. And he has said about how we can model it with different kinds of behavior. But if we would like to connect from one neuron to another neuron, so we need synapse. So basically, a synapse is a gap between neurons when they communicate with each other. So in that image, in the GIF image, we can see there is one neuron and it is connected to another neuron via some synapse. So when some action potential comes to the action terminal, so it releases some neurotransmitter. So synaptic input basically contains different kinds of neurotransmitters that might be excitatory or might be inhibitory. So here, if it is an excitatory neurotransmitter, so it will depolarize the cell as Kimshuk has mentioned through the sodium ion channel, and resultant membrane potential it will be increased. So you can see from the resting potential when there is a depolarization, so the membrane potential gets increased. And when it is a when neuron release inhibitory neurotransmitter, so that time it hyperpolarize the next neuron through the some chlorine ion channel, and it actually decrease the membrane potential of the postsynaptic neuron. So there are some underlying mechanism which we are not going through the details that how actually sodium channel and chlorine channel opens and closes and holds its state. So, but this is the very basic that for the depolarization, the membrane potential will increase, and for the hyperpolarization, membrane postsynaptic membrane potential will be decreased. So basically, we can model synapse with some exponential function or maybe alpha function based on what kind of action potential we need. Here we can see that this equation, and here J is actually the synaptic weight, and this is the exponential function, and it is the delta function. Actually, this is the basically takes the presynaptic input as a 1 or 0. Means if presynaptic neuron gets fired, so it will be 1, else it will be 0. So based on 1 and 0, the membrane potential, postsynaptic neuron membrane potential, that decay will be depends on that function. So here the tau is the decay of that synapse. So we can model this synapse with single exponential, maybe alpha, or with sum of two exponential function. So let's take an example how actually it works. So here we can see one excitatory neuron and inhibitory neurons, and they are presynaptic neuron. And this blue one is actually basically postsynaptic neuron. So if we just read out from this neuron, so you can see these are the membrane potential. So how actually it works? So when there is a excitatory neurons, so when there is a spike, so we can see here the postsynaptic neuron membrane potential gets little bit increased through synapse with some exponential function. When there is a continuously two spikes, so it crosses the threshold. So it reaches the threshold and it gets fired. So again there is some decay. So yeah, it decays, and after some time when you see the inhibitory neuron, the red one, it gets fired. So it, as it's basically inhibitory neuron, so it decreases the membrane potential. So there is a no spike for that. So when there is a excitatory neuron fires again, so again it start to increase the membrane potential. So like this way, the postsynaptic membrane potential depends on the presynaptic input spike. So this is very basically a basic synapse function, and it's called static function because the synapse weight does not get changed over time. Actually, there are much more complicated synapse function which actually consider nonlinear dynamics of the synapse, like reuptake policy function and vascular, how much the when neurotransmitter will come action terminal, so how the vesicle will be released or open. So those part actually is being covered in the dynamic synapse part or short time plasticity. So though in that function, they take or consider the history of the presynaptic activity. So actually they keep the memory or pattern of the presynaptic spikes for some, let's say for 5 seconds, 10 seconds, means it depends on our dynamics or application. So there are two kinds of plasticity. So that is short-term depression and facilitation. So here we have tried to give very simple example or illustration. Here we can see that when there is a spike, so the static synapse actually gives the fixed amplitude of the membrane potential increase. But when there is a facilitation, we can see the green one, it gets increased over the time based on depending on the function. And when it is a depressing synapse, so that function, the red one, blue one, it will be decreased over the time. So depends on our how we would like to use the function. So it will use the static, facilitator, and depressing synapse. So, so once we have the basic synapse model, so we actually would like to calculate how we can quantify those spike trend or phase synchronization, or in next slide we discuss that how we can quantify from the network. So here the first one is very basic thing, that spike synchronization. So if there is a two spike trend, if we read out from two neuron, yeah, if we read out from two neuron, and let's say the first one is firing pattern is like this, and second neuron fires pattern like this. So there we can see there is some spike synchronization between these two neurons. And we can see here also there is a burst synchronization. So these kinds of variation, if we would like to quantify, we can use the Fano factor kinds of measurement. And we can capture also the phase synchronization thing. Let's say because these two patterns actually are in 0-degree phase relationship. So we can capture this if we would like to quantify this measure. So we can use this phase synchronization, and we can see there's a 0-degree phase similarity, phase synchronization. So next one, that if we have some network where we connect some a group of n neuron ensemble, means here is we can, for the time being we can just ignore the name of the nuclei. Just we can assume there's a group of neurons and there is a group of neurons. They are connected with some synapse. The arrow is the excitatory and this was the inhibitory. So in these kinds of network, if we can just read out from this neuron, let's say there are 2000 neurons, so we can get the spike pattern, how actually 2000 neuron actually means generated. So in the x-axis, this is the time, and y-axis, these are the neuron ID. So here we can see when there is a spike, so it gives those blue dot, means there is an action potential gets fired, means that it reaches the threshold, so it gives the spike. And for this part, it is called PSTA. It's actually depict the rate and timing of the neural activity. Basically, if we just convert this into the Binning histogram, that is called peristimulus time histogram, so it gets these kinds of picture. And if there is some oscillation between these neuron of ensembles, we get synchronized pattern. So those neurons actually is firing with synchronous each other. So they give some oscillation. So when we see the PSTH, we can see these kinds of plot. Now, if we would like to measure the oscillation, so we can see here that in between means from this network, so there are some kinds of oscillation increased in the means here we have given some example that there is an increase of oscillation maybe for these kinds of plot, and but for this one we can see the green one there is a no oscillation. So we can measure these kinds of population response from this metrics. So here now we'll see that actually how brain networks works. In first slide, Kinshu has mentioned that how ANN and spike neural networks works basically with linear summation of the input and some function in sigmoid, and how actually we more or less know how actually in ANN the learning works with some back propagation. But in brain network, as we have seen, there are different kinds of heterogeneous neurons, and their firing patterns are totally different. We cannot match, maybe you can say, and their synaptic functions also are very much complicated compared to the ANN. So here, how actually brain networks learn? So that part will be discussed with Professor Arvind through the Zoom.
Thank you, Sangheeta. Hi, everyone. Sorry for you put me on big screen and I have to explain that I have one registered participant. He's going to sleep through, hopefully. And I do expect a little bit of disturbance from him towards the end of my tutorial because I think he is in his 40-minute cycle. And that's also a signal for me to finish my part. I should perhaps share my screen. Do you see it? So signal me when I can start.
Arvind, can you hear us?
Yes.
Yeah.
So can I start?
Yeah.
Okay. So thanks for this chance. I'm based in Stockholm, and as I explained, I have an unregistered participant with me, so I hope you don't mind that. He will sleep through mostly, I hope. So the plan for me that Kingshuk and Sangheeta laid out was to explain something about how we can implement function in networks of the brain. So I'm going to spend a few minutes on networks of the brain and then talk about what we mean by function. And hopefully I can also explain these terms again, even though Sangheeta and Kingshuk, they have already explained what excitatory inhibitory means. So as Sangheeta said, brain is not just neurons, it's actually a collection of neurons. And what we know as of now is that these neurons, they form very complicated networks. What these networks do is generate spike patterns that Sangheeta tried to quantify now. And those patterns carry information. This is all our behavior pretty much. So whatever we are doing will be encoded in the form of ensemble of activities. And this ensemble of activity must arise from the network given certain inputs. And that's, I think, personally, for me, that's the crux of neuroscience, to really understand how networks give rise to different kind of spike patterns which get attached to different behaviors. So when we look into the brain, we get different kind of networks, and it really depends on at what scale you want to look at. On the far left here, you see a network which is extracted from mouse brain. There they measure connectivity between, let's say, 50 to 100 micrometer volumes of the brain, how that one volume is connected to another, and we get a complicated picture. The message here is that it's not random, but it's also not hierarchical or feed forward in the sense that information enters through senses and comes out through motor cortex. If we look further into these modules, you find that some brain areas, at least, they have very distinct structure. There are anatomically segregated regions, like here, for instance. This is an example from a brain area called cerebellum, where you can distinctly see different anatomical landmarks which separate different modules. In the neocortex, which is a relatively new invention in the evolution of brain, there we find more like distance-dependent connectivity, meaning neurons connect according to some rule which decides their connection probability as a function of distance and neuron density. So in the top, you see distance-dependent connectivity in the horizontal plane. In the bottom, you see connectivity in the vertical plane. And then there are some other curious features which reveal that this distance-dependent connectivity is not always going down. Sometimes it can come up in the form of these patches as well. And if you further zoom in into the brain, you will meet what is called the canonical microcircuit. So there are deep layers of the brain, superficial layer of the brain, and they are connected. So mostly these layers are described in terms of excitatory neurons. And there are interneurons which are connected mostly within the layer. Therefore, they are interneurons. And typically they are inhibitory. So they create a specific circuit in the deep layer, a different one in the superficial layer, and then they talk to each other. Information arrives in the superficial layers, it gets processed and then sent back to the layer T5 where it gets exported to the brain. So depending on the scale, you will meet different kind of networks in the brain. Mathematically, if we want to describe them, we can think of them as feed-forward networks, or a completely random network, or a random network with some distance-dependent signatures, or a distance-dependent network but with local patches of some sort. Most of the machine learning, as far as I know, is about feed-forward networks and a little bit about random networks in the name of RNNs. So all these architectures, I think they haven't been tried. And I mean, as neuroscientists, we don't know what this means to have such local connectivity or patchy connectivity. Now, if we go back here and just start with a completely random network, it's not that these networks are unfunctional. It turns out that a random network, just because you have wired neurons with some fixed probabilities, it still has a lot of interesting functions that emerge even without training it for any specific cause. So here is an illustration of a random network, and here's the graph of that. Again, excitatory inhibitory neurons, red and blue. These kind of networks, if you bring them into what is called balance regime, where excitation and inhibition are balanced so that this network remains stable, a lot of functions arise which are useful. For instance, these networks are very good at tracking inputs, very fast inputs. Kingshuk showed us neurons have time constants, which means they are slow devices, but as a network is arbitrarily fast. They get invariances of some sorts. In many cases, for instance, in visual cortex, they get contrast invariance, meaning response doesn't change. If you change the contrast, you can normalize signals, you can amplify, and you can show attractor dynamics, which form the basis of working memory, etc. And just to give you a glimpse of it, so this is an example of amplification. Again, it's not an amplifier that we design as an engineer. This is just collection of neurons randomly wired to each other, and the whole system brought to a balance where excitation roughly cancels out the inhibition. You give it an input which looks like this. This is called tuned input because this input is slightly higher for certain orientations and then weaker for other. If you now pass it through and you measure the response, you get actually much, much finer tuning of the neurons. The input was tuned like this, like in the green circle, which tells you that it responds slightly preferentially to a vertical stimuli. But after you have passed it through the network, what is left is vertical tuned neurons, more or less. Some neurons have other tuning as well. And this is what we mean by amplification. So what actually is happening in this network is that this network is very good at subtracting this average and amplifying the fluctuations. And schematically or conceptually, we try to think of it in terms of a control system, for instance. Maybe most of us are familiar with this kind of block diagrams that we study in first course in control engineering. So here we have a stimulus, and this is the block we call as the network, which has some feed-forward gain, and then there's feedback in the form of inhibition. Turns out it makes sense to break this down into something called average component and a modulation component. And this we can do simply by looking at the eigenvalues of this connectivity matrix. And the whole network then is described by this amplification, by this factor gamma. So whatever stimulus comes in, it will be scaled by gamma, and that will be your response. Turns out, if you start with weak synapses, gamma is in the modulatory part, it's very big, and that's the basis of this amplification that I talked about. All you need to make sure is that the beta is negative. So effectively, this network operates in so-called inhibition-dominated regime, meaning, as I said, we have excitatory and inhibitory neurons. They are not properly balanced. Inhibition is slightly stronger than the excitation. You may wonder why this network remains active. Because we are thinking of stochastic input, there is always some fluctuation that drives the network. So in a way, we are working in fluctuation-driven regime, inhibition-dominated regime, and then we get this nice property of amplification that you see. There are other classical behaviors of these networks. For instance, working memory models exploit the attractor dynamics, meaning these neurons, the network have this property that once you connect them in distance-dependent manner like this, what you get is the activation of some group of neuron latches the activity within that group, and it remains active unless you perturb it. So classical dynamical system, an attractor-like behavior, give it an incomplete input, and it will complete it and remain active unless you perturb it. And these kind of models people use, for instance, to explain working memory duration, how we store some transient information in our brains. Also to explain certain curious behaviors of the brain cells, for instance, grid cells, where an animal runs around in a circular arena, but neurons are becoming active only at specific locations. So that also exploits this attractor-like behavior. But this is something that we get for free almost. You just wire things up, connect them with, let's say, fixed probability, balance excitation inhibition, obey the rule that neurons are distance-dependent connected, and that's it. What about something more sophisticated, something like controlling a robot arm or things like that? So in neuroscience, as far as I know, there are three main paradigms how we construct networks. One is called efficient coding network. Others are called neural engineering framework and echo state network. I will spend some time on efficient coding network and then try to argue that other two are actually the same and see what we can do about this. So here is a problem. So Kingshuk spent a lot of time explaining spikes. In the machine learning literature, we don't work with spikes. We don't know how to train those networks very well. But when we think of the brain, all we record is spikes. And typically the spikes, they look very, very random to the extent that they can be approximated to a Poisson process. So on one hand, you have Poisson spike. On the other hand, you have regular rate code. If you look at how many spikes are needed and how many spikes will fire, of course, there will be a distribution with Poisson. You will always have a higher variance as you increase the rate. So if you set the spikes to 6, regular code will have 6 spikes, but a Poisson code will have 6 plus the variance will also be 6. In these cases, if you compare the coding error, it turns out that with regular spikes, you do much better as opposed to Poisson spikes. So turns out that the Poisson code that we seem to think exists in the brain may not be an optimal one, at least in the form of how it scales with number of spikes and the error. So something else is needed, and something else is needed which exploits the relative timings of the spikes. Because if we are counting the spikes, then we are essentially converting a discrete variable into a continuous one, and then we can use the whole theories of nonlinear dynamical systems. So the key question here is that how to exploit the spikes. In particular, can we say something about spike times? And what kind of networks come there? So the main idea behind efficient coding is that we want to construct a network which, given some input, produces certain output. This input gets mapped onto the network with some projection matrix K, and it's read out using the matrix phi. Now, since we are designing this, we can say that maybe I know K, maybe I also know phi, and I definitely know my C and T because I want to train this. So the only unknown in this setting is omega. And omega, of course, will depend on the dynamical system you want to put in this network. So that's the problem statement, more or less, that given some A, K, and phi, how to construct an omega, which makes sense in the form of like it resembles the brain network somehow, and it exploits spikes. Like that's the reason I'm even schematically displaying spike trains here, which eventually get filtered to construct my target signal. So let's start with a very, very simple example. There's nothing here except that there is some input, some output. So X gets converted into X hat. We have N neurons which project this X. So each one gets the same copy of X, but they are all Poisson neurons. Some noise is added. So each one spikes like this, and we sum these spikes out and get our X hat. So there's no recurrent connectivity here. We have a lot of spikes happening. And you could say that, well, there is little variability because I'm summing up over many, many spikes and many neurons. But in a way, I'm wasting spikes. So my spike times don't matter. And I could as well have thought about a rate signal, a continuous signal. So to make spikes count, what we can do is do something like start inhibiting these neurons. So inhibition, as Sangheeta explained, hyperpolarizes the cell. So meaning if this neuron receives inhibition, it will not spike for some time. And we can construct some kind of winner-take-all dynamics here, that whichever neuron spikes first, it inhibits others for some time. And after that, whoever gets its turn to spike randomly takes over. Now, what we get this way is that very sparse firing. And because of this winner-take-all connections I have put in, every spike counts. And I need all the neurons to construct X hat. So if one of the neuron goes missing, I will start to make it. So that's the kind of notion we are going to use to make spikes count, or not spike count in the sense of numbering, but have a weightage, meaning the spike, the time has a meaning. So we can scale this problem a bit up to a multidimensional system. This was one-dimensional. We can make it multidimensional. And now, of course, I need K and phi, and those K and phi you perhaps heard earlier. Essentially the same task once again. So you project it and you want to construct it. So that's the idea we can use to construct omega, that my C maps to X hat in some optimal sense. So now I can revise this terminology. This is my feed-forward matrix. This is the decoding matrix. And this network will have some rate, which I'm going to construct using by filtering the spike train. So this is some internal variable I will use. And eventually X hat will be constructed using spike trains as well, once again, by filtering them. So as standard definition, we can apply that, let's say I want my X hat to closely resemble this particular dynamical system. I can define a cost function. And a standard way to define a cost function would be to have minimize the error or the mapping between the target and the actual what we saw. But in addition, because we want to make our network where spikes are important, we could say that the spike should be sparse. Moreover, every neuron should contribute something. So we want to have distributed firing. So you have a normalization term, regularization term. So this is L1 norm and this is L2. And then we make another interesting point here, which is that a neuron spikes only when there is an error, so that we can try to track it as closely as possible. For that, what we do is the following, that we think of this whole matrix and note there are no connections here. It's just a bunch of neurons, nothing is happening. It's exactly our toy problem. All I'm doing is subtracting the estimated signal from the target one, and only the error is fed back. And if we do this setting, perhaps you remember control engineering, you could replace that branch and absorb these connections within the network itself. And in this case, an optimal omega, of course, as you do some little bit of linear algebra, you will come to the point that omega should be equal to negative of k times phi, which is that error is mapped by k, then it is going to be mapped by omega, and then mapped by phi. So we have to reverse that, and this is how it should be. So this is how we can absorb this feedback branch within the network. So at least we can construct a network which is now driven by error, and we have some notion of connectivity there. So all we want is feedback. Again, if feedback is inhibitory, again, we are thinking of an inhibition-dominated region. Now, how do we think about formulating this network? So what will happen in this network is, meaning what else is needed? We need to do some more tuning of or calculate some more parameters which relate to the neurons. So we have constructed omega, but we don't know what are the parameters of the neuron, and in particular, we don't know the spike thresholds and if they are important or not. So I'm not going to do the proof, but I'm just going to give you an idea what is behind this calculation. The idea is the following. Let's just say that there is some input that comes in and this network is operating and a neuron spikes. What will happen if a neuron spikes? This neuron will perturb my X hat by a small amount plus the filtering that I'm at. And what we want is that a neuron spikes to minimize the error. So that means that I want to make sure that the error before that spike is greater than the error after the spike. Yeah, so that's the formulation of the problem, if you wish. So we want that each new spike leads to a reduction in the error compared to the previous one. So we can't really look far in future. That's not possible. We have to set some horizon, and usually that horizon is decided by the time constant of the membrane because we can't go any further. If you follow that and expand the error terms, what we come to is this kind of inequality. So this is my projection matrix, readout matrix, if you wish. This is the error plus some regularization, which is taking care of the firing rate. This should be greater than this one, which is another normalization, which was taking care of my sparsity. So mu is for sparsity and mu is for distributed firing. So how distributed we want and how sparse we want. Plus these are time constants of the neuron, and this is the projection matrix. So this side, if you notice, is actually constant. We know phi, we know mu, we know nu and tau. And this side is changing over time. Depends on the error, right? So one analogy we can make now is that we can treat the left-hand side as the membrane voltage and right-hand side as the threshold. And this takes care of the fact that actually spikes occur. If they cross this threshold, there's a spike, but the way we have derived it is that this spike will lead to a reduction in the error. So if we let this evolve, sooner or later, my system should converge. So this way we can set up, starting with this cost function, we can say that this is the membrane potential, and this is how the spike of the spike threshold of the neuron should be set, and we are done then. Then we have a full description of this network, which takes care of mapping this signal CT to X hat. And of course, you can derive the dynamics of the neuron, how each individual neuron will behave. So there is some leak term plus the contribution from the network and the feedbacks. So phi t here is basically k, right? So this is phi transpose. Okay. So this is how this system is going to work. And now we are sure that this network will follow some dynamics, which we want it to follow in X hat. How do you think about this? I very hand-wavily told you that the membrane voltage is like an error term, or it's related to that. The way we think about this is that because we have absorbed this connection inside, what we are seeing is that each neuron is representing one dimension of the error. So this is one way to visualize it. And whenever that neuron spikes, it minimizes the error in that particular direction. So think of your dynamical system with n dimensions. You're going to make error in each dimension. Feedback comes in, and the neuron now records in which direction how much error has happened. The moment a neuron spikes and resets, at that point, error in that dimension is reduced. So this is how to visualize this. And this is a very nice visualization that you can find in this paper by Deneuve and Watkins. This also leads to a very nice analogy that if we structure the network like this, neurons automatically will end up having tuning curves. Tuning curves means that neuron only respond to a specific class of input. Now, how do we think about this? This network, these kind of networks actually have very interesting properties. And one very relevant property is the so-called robustness. And for that, we have a very simple toy example. So think of this network where there are two neurons, R1 and R2. They are driven by some X, and we want X hat. And X hat looks like this. So because the way you derive the connectivity for this, it turns out that you are going to operate in this winner-take-all setting so that you have sparse firing. If everything is intact, one of these neurons will spike because they have this winner-take-all competition. If I remove, so in the normal case, either one of them is spiking at every time. If I take away one of the neurons, then this winner-take-all circuit breaks down and only this branch exists, and then only one neuron takes over. So not only that the network is sparse, but it is now robust to these errors that some neurons will be lost. And indeed, in brains, we lose neurons. Not this little one, he is actually perhaps growing, but people like us, we are losing neurons at quite high rate. So in that sense, we can remain robust as well. And there are now follow-ups of this idea, which you can then use to exactly implement some kind of dynamics in it. So for instance, you can have a certain dynamical system, which is here in the form of a continuous dynamical system, which you can now scale also with other nonlinearities of the neurons. For instance, this G could represent nonlinear dendritic integration, etc. So in this case, we have this one, this branch that takes care of the sparsity, and this branch takes care of the dynamics, the particular dynamical system. And when you derive it, you can say that my network connectivity has two kind of connections. One very fast connection that take care of the fast connections that take care of the sparsity, and the slow connection which take care of the dynamics. And this is how you can derive omega for dynamical systems. So you know the projection matrix, you know your A, time constant, and so on. And for efficient coding, this is better. So this is how you can schematically describe networks like this, and one by one, absorb the contribution of those branches in the recurrent connections. You can add a teacher signal if you wish, the same deal. You just keep absorbing them. Here's an example how this network is behaving. For instance, this is an example of an integrator. So each row is a neuron. Each dot is a spike of that neuron, and X and X hat are blue and red. And these are the firing rates of the neurons, two example neurons. So you give it some input, it starts to integrate, it holds it, and it again integrates, and so on. So you can construct an integrator, you can construct a two-dimensional system. So now this is my dynamics. So if you know what dynamical system you want, you can exactly calculate what should be the spiking dynamics, what should be the time constant and omega, and then you can get this nice behavior in this model. Again, leaky integrator, leaky differentiator, damped oscillators, all these various well-defined dynamical systems can be included in the dynamics of the network. This is one aspect. And here, as I said, that you need to know the dynamics that you want. Typically, that's maybe not available to you. So there's another class of models which are called echo state networks. In echo state network, it's basically an idea about RNNs, that you have recurrent neural networks. If you tune them close to their critical point, close to their stability border, they exhibit interesting dynamics, and then you can read out their dynamics, learn these projection weights, and get your target signal. There are other variations as well, and they are very good in the sense that any arbitrary dynamics, you can train them for. Here's an example for a continuous one, but later, I think from Klopath and Nicola, there was a very nice paper where they talked about the implementation of this force training in a spiking case as well. So that exists. There are three frameworks, as earlier I indicated. One is this force, the efficient coding, where I spent some time on, and neural engineering framework that I didn't talk about at all. So my only contribution to this work is that we found out that actually these three things are basically the same thing. So let's write down the dynamics of the network. We write it down like this, that there is some neuron which has a leaky dynamics. It receives some input and some feedback, and feedback is as it is, right? We formulate it in the same vein as we did. There's omega, there's a readout matrix phi, there's a encoding matrix k, and we can make as high. This is the dimensionality of the dynamics that we. So this is basically the feedback. Now, when we think of the echo state network and do the force training, what we are actually doing is that the input that is going into the, oh, by the way, in this dynamical system, you can also change it, put some desired dynamics, and that gets absorbed in the connectivity omega. So this I that is going in, there are two components to that. One component is recurrent and one is feed forward. Feed forward is basically the K and phi together. So in force learning, what we do is that we assume that omega is constant, K is constant, phi is changed. And phi is changed according to this. So if you change only this, the decoder, then you have a setting which is force learning, and this allows you to use arbitrary signals. If you use neural engineering framework does something else. It has exactly the same setting, except that in this case, we don't have any feedback. We have a drive, right? So you assume that omega is actually 0, and all you have is this k and phi. And you do this argmin calculations to construct your phi. And k is indeed a transpose of phi. So that's another generalization of this particular setting here. And finally, efficient coding, we already saw that in that case, we assume that the recurrent connections are very, very fast. And this W takes care of the time. Okay. So in a way, all these frameworks, they basically rely this architecture, an encoder, a recurrent network, a decoder, and a feedback. Depending on where you focus, you will find papers on that particular. Now, this is all about learning. As I said, there is now a paper which talks about how to train these networks in a more for a spiking case. But also for the efficient coding framework, there is a rule which allows us to derive some connectivity, basically exploiting intrinsic plasticity rules of the brain to learn those recurrent weights and feed-forward weights. I don't have time to explain how you derive this rule, but the main idea is that, as I said, in this case, what is happening? Membrane potential is carrying the error signal. What you want is that the error should expand the whole dynamical range. So if it has accumulated some error over time, the spike that comes in, that should try to reset that error. And if that spike comes from an excitatory neuron, it should take it close to the spike and then reset the error. If it is inhibitory, then it should directly take it to. So in one case, you want to hit to the spike threshold as quick as possible. In other case, you want to reset. And that leads to this rule where the change in a particular weight depends on the spiking output, the distance to the threshold, and the current weight. And this is similar for feed forwarding. And there are more variations of this, and maybe we can spend some time discussing that on another occasion. So this is roughly how you can construct a network which does something useful. And useful, it does in the brain sense by exploiting spike times, and spikes are important for this network. Neural engineering framework force are not necessarily spike dependent. They can be done with continuous variables as well. efficient coding, I think, to the best of my knowledge, is the only framework where spikes are important. Therefore, I thought it's worth talking about that. Right, and I think I will close with that. I won't show you anything like Kingshuk did because I have additional things going on. But I want to then say a few words like how this kind of theory that people are developing, including ourselves. So we are working at this level, pretty much building theories and using these theories to explain, let's say, function, some brain statistics. But actually, this has much more value because if we think about brain diseases, obviously, most likely they start somewhere in the hardware of the brain. They get manifested through the, you go to a clinician, they will diagnose these diseases. But if you will eventually ask them, what is this? Then they will say that there is something wrong with the hardware of the brain. Or maybe firmware. Hardware meaning genes, neurons, firmware meaning chemistry of the brain. But eventually, all this will be reflected in the brain activity. And I think we would like to claim that by understanding the theory of these networks, theory of function, we understand also how these brain hardware level changes reflect in the brain activity. And therefore, we can create these model-based simulations of the brain, of the disease in particular, and hopefully we can control or correct the diseases. And this is what Sangheeta will take from this point. And I again apologize for the background noise.
Thank you.
I'm happy to take questions now or later as the schedule allows.
Some kinds of technique that how we can read out
Sangheeta, is there a question?
Arvind will take it later. The computer modeling. Arvind, can you hear us?
I didn't hear properly. Could you repeat?
Yeah, we'll take it later in the session.
Ingchu, can you unmute yourself?
So till this point, we have developed the basal ganglia model for which can generate the healthy as well as Parkinsonian disease state. Now we will use our model or use our knowledge to build a model that can explain the brain activity. Now assume that in PD case, you have seen the PD case, the beta band oscillation is a cardinal feature. And cardinal feature, and since in PD you can see oscillation, we can expect to have some high frequency component, right? And now we assume or we hypothesize that this oscillation comes from the change in excitation and inhibition inside of some brain region. Now, in order to capture this, our researcher from KT Sweden captured the MEG activity from the scalp of PD patients as well as from healthy controls. Now, MEG is basically the electrical activity that gives you the spatiotemporal dynamics of the brain in a non-invasive way. Now, once you have that activity, you can then do the frequency domain analysis using Welch or any other popular methods based on some window with some overlap. This will give you basically one of the frequency plots for a particular window, and based on this frequency plot, we feed a FOOF algorithm. We do the FOOF analysis, and FOOF will give you the slopeness of the curve, and it will give mainly the kappa and lambda parameter. This lambda will give capture the high frequency component. Less the lambda value, we can say more the high frequency component. So in PD case, we expect to have some less lambda. So now here you can see the MEG response from the different parts of the brain. In PD on and off is basically the PD on means PD with some medication, and off means PD without any medication. But the person in the PD state, you can see there is no significant change in the lambda values. But when we compare with the PD on or off with respect to the healthy control, you can see in some parts of the brain, there is yellow dots, there are a significant difference. That means in PD case, the lambda values decreased a lot. That proves our hypothesis. Now question is, we were very curious to see what goes inside in the microcircuit level. For this, we model the basal ganglia, but using a small part. For example, striatum, globus pallidus, subthalamic and external input. It's a small part of the basal ganglia with some leaky indicate fire neural models. And just for the time being, assume that when the striatum sends the inhibitory signal to globus pallidus, it induces oscillation as well as Parkinsonian state in the network. Just assume that. Now, if we increase that inhibition, then oscillation will also increase and PD state also get more severe. This is the assumption if you can make right now. Then what we did, we changed the network parameters. By network parameters, we mean the synaptic weight, connections, delays, and background inputs, and also gradually increase the striatal inhibitions. And for each one of the network configuration, we computed the oscillation index and the exponent values or the lambda values. We can see from this figure that in most of the cases, or in very few cases, there is a transition from the low oscillations to high oscillation or high exponent to the low exponent values. It means that the situation is not very straightforward. In most of the cases, the transition happens only in the left half of the low, that means low to low oscillation and high to high oscillations. So from there, we can conclude, or we hypothesize, or we can claim that these transitions or the excitation inhibition balance depends upon the initial network state. And this initial network state is nothing but the patient's initial brain state. So from this last part, you can see how you use the data to derive, to prove our hypothesis partially, and then use that hypothesis and build our own network model to derive more insights. So in this tutorial, I would like Professor Arvind to just conclude the tutorial for today. Arvind, can you hear us? Hello?
Hi, Kingshuk. I think I will share it on my end then, because I
Okay.
can barely read your slides.
Okay, okay. Yeah.
Do I do that? And how do I play this?
Yeah, we can hear you.
Okay, great. So yeah, this tutorial was suggested to this meeting, which is pattern recognition and so on. And then we were thinking, like, what does it mean? I thought what we wanted to do with this is to give you some overview of like what neuroscience is doing, how you can bring in engineering solutions. But just to conclude, I think brain fascinates engineers for various reasons. And few of them are because one is it's highly power efficient, it's excellent at generalization, and as far as we can say, it learns from very few samples and doesn't show any catastrophic forgetting. All these things our AI applications demand heavily. Now, there is a general feeling that you can learn something about the brain and implement these things in modern hardware as well. But there are serious challenges. One is that we don't know good learning rules for spiking neurons. And the main hurdle there is that they are not really differentiable neurons. Other issue is that for the brain, as far as we know, brain uses local learning rules. There are suggestions how backprop, etc., could be implemented, but they are just, I would say they are not very serious attempts yet. And finally, if you even want to work with spikes, then I think most people agree that they don't even have that killer app which will actually drive industrial interest in this. So I think these would be some challenges that engineers can address. On the other hand, brain science needs engineers because as Kingchuk and Sangheeta were describing about Parkinson's disease, that's just one example. There are many diseases where you need various kinds of sensors and data analysis algorithms to monitor patients. And the second thing is that as we gave you example here, several diseases can be thought of diseases of dynamics like Parkinson's, but also you can use frameworks like reinforcement learning to think about psychiatric disorders. And there are a lot of engineering solutions that exist that could be useful for brain science. Of course, it's not that straightforward because as engineers, we are used to thinking of different layers of integration, for instance. The big challenge in the brain science is that we don't really know what is a good readout of the brain activity. Different people have different opinions. Other challenge would be that how to think of the brain as a multi-scale system. There are scales, but it's non-trivial to define those scales. So I think there is a lot of room here for engineers to come in and have a mutually beneficial relationship with neuroscience. Yeah, that's all that I wanted to add in the last few minutes. Thank you.
Okay. Thanks, Dr. Arvind, Dr. Sangheeta, and Dr. Koki. So we are running out of time, but as Dr. Arvind is attending the meeting, what is there any question for Dr. Arvind? Then you can ask right now. Can you
Was it a question for me? I couldn't hear. If it is for me, it would be best if you can type it, please.
Hello, Professor. Can you suggest some books so that somebody who doesn't read about this and get acquainted with the idea? maybe making introductory book on your subject.
Interesting books. Could somebody repeat the question, please? I think it would be best to
The
type it.
question is, he's asking for some introductory books in computational neuroscience or neuroscience only,
Oh yeah. So there
and
are
neuroscience both.
several books at different levels. The classic that we often refer to our students when they come to neuroscience from engineering background is called Theoretical Neuroscience by Diane and Abbott. It's a bit fast, this book, but covers a lot of ground. I would say that's a good starting book. If you want to venture into theory part, if you want to get into more experimental part, there is a particular book I like a lot. It's called Exploring the Brain. It's a textbook and written in a very enjoyable format. But there are more. I mean, we can provide you lists at some point. There is also a tutorial. Actually, maybe that's even more useful. Since I'm sharing my screen, I think I can show it to you and post the link.
Question. First, thank you very much for your talk. My question is whether this was taken into account the more understanding of the importance of neuromediators. So that neurons are not just wires. Interwired. They exist in an environment which is filled with neuromediators. So does your model take into account this, or can it be adapted to this new knowledge about neuromediators?
Sorry, I didn't really understand the question. Could somebody repeat it, please?
Question is the neuromediators.
Yeah, whether we are taken into account, or if not, how can
Sorry, it's echoing. It's echoing a lot.
Yeah, so the question is regarding the importance of neuromediators, whether the importance of neuromediators and whether your system can accommodate all those neuromediators.
Neuromediator, I suppose you mean neuromodulators.
Neuromodulators, right? Yeah.
Yeah, so neuromodulator is a very different game. It is true, they are very powerful and brain has all kind of ways to distribute them. What is unclear is, for instance, in this framework, the way we think about that, something is excitatory or inhibitory, that distinction becomes very blurred when you have neuromodulators. There are reductions for specific situations. Like, for instance, for this particular situation of Parkinson's disease, there is neuromodulator, and that neuromodulator enhances or suppresses the synaptic strength or gates the plasticity. So this is how you can capture the effects of different modulators. But it's a very difficult question to address. Yeah. Parkinson's disease is actually a great example where this is explicitly modeled to explain the disease phenotypes.
Okay, thank you, Dr. Arvind. So Dr. Sangheeta and Dr. Kingsuk, they will be available here. So if you have any question for them, you can continue the discussion. You can discuss with them during the tea break. Thank you. So let us thank all the three speakers, Dr. Arvind, Sangheeta.
So I have just posted a link in Zoom. Maybe you can distribute. This is a link to a video series that we created 2 years ago. And this gives you a very nice, easy entry into neuroscience. There are different kind of lectures for different topics that we think are relevant. So you can check.
Share that link through email, or you can share it in the Zoom chat
In
also.
Zoom now. It's in Zoom.
Okay.
All right.
Okay, so they have copied it, right?
Yeah.
Okay. Thank you, Dr. Arvind. Thank you.
So